Good morning, everyone. Hopefully you did well on the exam. I don't know if I'll have grades back by this point or not, but hopefully I do. Um, Today should be the 28th when you're watching this, and we are diving into chapter 6. Chapter 6 is really where we start to learn our reactions. So knowing what an electrophile is and knowing what a nucleophile is at this point becomes crucial, critical. You need to have that information down by now. All right, so let's get started. So, as I mentioned, this chapter is alkyl halide, alkyl halides, nucleophilic, substitution, and elimination. Let's break that down. So alkyl halides, we talked a little bit about them. We actually learned some naming. We're going to review that today as part of this lecture. So alkyl just refers to any sort of carbon chain. You can put branches on it. You can add different groups, whatever. Halides are your halogens. So commonly abbreviated X. Those would be your chlorine, bromine, and iodide. Fluorine is one of them, although we typically don't use it as organic chemists, at least not an organic chemistry one for undergrads. All right, so we put those things together. Alkyl halides, we have some sort of organic compound, carbons and hydrogens, just all uh, carbon hydrogens. And then let's see here, let's do this. Add a bromine. Now we have an alkyl halide. We talked about how alkanes are typically quite unreactive, but last chapter we started to talk about this radical reaction, and there's 3 steps to it: initiation, propagation, and termination. We're going to review all those as well, where we can now take an alkane and add a Br to it using a free radical reaction. So when we add this alkyl bromide onto our hydrocarbon, we've now created a dipole, because remember, your halogens are more electronegative than carbon. So this has a partial minus, this has a partial positive. This gives this carbon some new abilities that it didn't have before. So let's take a step back. Let's try to name this molecule. Go ahead, try it on your own. I'm going to go through it. We want to find our longest carbon chain. We could have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We want our first substituent at the lowest number. So I'd probably start here. That's where our bromine's at. So 1, 2, 3, 4, 5. Feel free to number. So I'd like to take things kind of step by step and then combine them all together. So we have 1, 2, 3, 4, 5 carbons. So we have a pentane. We have 1 bromo, 2 methyl, 1, 2, and 3 ethyl. So now we want to put those in alphabetical order. A, B, C, D, E, then M. So putting them in the correct order, we should have 1 bromo. Remember, anytime you're in between a letter and a number, there should be a dash. 3 ethyl. 2 methyl. Oops, almost forgot my dash there. Methyl pentane. Hopefully that should be review. We're going to do another practice or two just to make sure that's something you're remembering. So, and of course, bromo, abbreviation, when we have a bromine, it's bromo. When we have a chlorine, chloro. And when we have an iodine, it's iodo. So let's do 2 more practice problems. Let's try this one. I won't make you include R and S in the name here, but I would expect you to know what type of isomer, or excuse me, what type of conformation this is in. So again, pause, try it on your own, and I'll start writing it out. So we have 6-membered ring. So it should be a hexane. From there, we have two iodos. So we're going to start wherever we want. I'm going to start at the top. 1, 2. We also are in a ring, so we should have cyclo. 1, 2. So 1, comma, 2. In between numbers, there should be a comma. In between numbers and letters should be a dash. Because there's two of them, we get the prefix di, iodo. So 1, 2, diiodo cyclohexane. But we're forgetting what type of conformation this is. I'll move the paper up in just a second. 1, 2, iodo cyclohexane. So hopefully we just finished the chapter on stereochemistry. We should feel very comfortable and confident about this. If one's on a wedge and one's on a dash, how are they related? Are they cis to one another? Cis being the same, or trans? This would be trans. So it'd be trans 1, 2 diiodo cyclohexane. Hopefully that wasn't too tricky. All right, let's do one more practice. This time I'm going to throw an alkene in there because I believe we did talk about alkenes. So let's do this. All sorts of practice with this one. So pause it, try to do this on your own, try to name it. I'll go through it. So finding a large carbon chain is the first step. Shouldn't be too tricky with this one. 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Okay, so this part might be a little bit more tricky. We got to determine which side we're going to start at. Typically, we want our first substituent at the lowest number. In this case, our first substituent would be from this side. But when we have new functional groups, which we're going to get into more details with that, with our double bond here, that actually has higher naming priority than all of our halogens. So our alkene, remember, would have higher priority. So we're going to want to start the chain at our highest priority functional group, which in this case is our alkane. So 1, 2, 3, 4, 5, and 6. So remember, there's two different ways to name alkenes, the old way or the new way. I'm going to go about the new way. So we should have a hex. Our double bond starts between carbons 1 and 2. So hex 1-ene is what we would put for our base name. From there, we have a 3-chloro, a 4-bromo, and a 5-iodo. Now I'm going to put that together in the proper alphabetical order. So our total name should be 4-bromo, 3-chloro, 5-iodo, hex 1-ene. You could do it the older way too if you're comfortable or more familiar with that. All right. Hopefully this was maybe a little bit more challenging, but these are things I would expect you to be able to do. All right. So let's talk about the halogens quickly. We know a lot about alkenes. We spent a lot of time talking about them. But let's talk about our halogens. So there's 4 in total. 3 we really focus on. Fluorine, chlorine, there's actually more than 4. Bromine, and iodide. Fluorine is the smallest, and it's also the most electronegative. Hopefully you got that right on exam 1. Chlorine is a little bit larger and kind of a middle electronegativity. So it's a little less, or no, that one's a little more electronegative than this one. So you're going to see kind of an opposite trend here. As we go down the periodic table, this gets going to the right, but if you look at the periodic table, we're going down. The size keeps getting bigger. With iodine being the largest. In terms of electronegativity, though, the electronegativity keeps going down. So iodine, although it's the largest, has the lowest electronegativity. If you are ever to, I'm not going to ask that, so I'm not going to bother. Just for maybe your homework will have it though. You ever come across fluoro on a compound or fluorine? It's just fluoro. ORO? FL. Yeah, exactly. I'm never going to ask it because I'm pretty sure it's fluoro. Yes, that looks right. Fluoro. Oh, wow. So there's our halogens. For some reasons we're going to talk about, the reactivity of these halogens are different than one another when they're attached to an alkane like this. For our purposes, fluorine and alkyl fluoride is not reactive. A few different reasons for that. I'm not really going to get into it, but the trend is what I care that you know. As we go further down, we become more and more reactive. This is reactive. This is quite reactive. This is very reactive. This has to do with something called polarizability. So, which is kind of related to size. In this case, fluorine, if we were to kick that off, and we'll talk about that in a second, if fluorine were to leave a carbon, so let's use this as an example. If our fluorine here was to just take its electrons and leave, we'd be left with something that looks like this. Positive charge on our carbon, and now our fluorine has 8 electrons around it. And although it's very electronegative, it doesn't mind being in this form, but due to polarizability, it doesn't love it either. So what do I mean by polarizability? Because fluorine only has so many protons, less than chlorine, bromine, and iodide, how do I want to explain this? The charge here is a lot heavier. Imagine a very small person. I don't know why I'm up with refrigerators, but imagine a very small person trying to carry a refrigerator. Chargers are just refrigerators for some reason. A very small person trying to carry a refrigerator, not going to work. But as we get larger and larger in size, maybe bromine's a little bit stronger or bigger of a person, because it has more protons around it and more electrons too, it doesn't matter. It can hold on to that negative charge easier because it's weight-wise, if you want to think about it in terms of our simile here, it's a little bit easier. The person has a little bit more muscle, they're a little bit bigger, it's easier to carry that refrigerator. Then iodine, it is so massive, it can lift that refrigerator with one finger. That's the kind of idea I want you guys to have. Iodine can hold on to a negative charge very, very easily due to its size, not its electronegativity, because that trend is the other ways, right? This is our most electronegative atom. This is our least. I totally skipped over chlorine. I apologize. But the trend is the same. Chlorine really doesn't want to hold on to it in terms of polarizability. I should write that word down. Polarizability. We'll define that in just a second. Iodine is super polarizable. Bromine's a little bit less. Iodine's a little bit less, and fluorine is so small it's not very polarizable at all. So because of that, whenever you have an iodine bonded to a carbon, that reaction is going to go much, much faster than a chlorine. And for our purposes, fluorine typically doesn't react at all. Give me just a second. Okay, let's look at some examples going the other way. We've named a few compounds, but if I give you the name, I also need you to be able to draw the structure. So let's look at a few examples. Let's do carbon tetrabromide. Although we haven't talked about the specific way of naming, I bet you could figure that one out. And then I'll give you one that you're more familiar with. So carbon tetrabromide and 2,3-dichloroethane. Take a second, pause the video, try doing those out, and I'll start writing it. So carbon tetrabromide is what it sounds like. It's carbon with tetra, meaning four, just like the game Tetris, all those blocks. Each block shape is made up of four smaller blocks. Fun fact about Tetris, if you didn't know. Carbon tetrabromide has four bromines attached to it. Oops. Where 1,2-dichloroethane, ethane is just two carbons. Oh, I said 2,3. That name's no good. Do, oh, it's gonna be easier to change here. Probably just 1,2. I apologize. So 1,2, carbon 1, carbon 2. So dichloro means we have two chlorines on the 1 and 2. Let's try one more practice. This one will make it a little bit more challenging. I got smaller at the end. 1 bromo, 3 isopropyl, cyclobute, 1 ene. Pause it, give it a try, and I'll start writing it out. So cyclobute, we have a ring. Bute is 4 carbons. Cyclobute 1 ene. So between carbons 1 and 2, we should have a double bond. So this will be our carbon 1. This will be our carbon 2, 3, and 4. Now we need to attach our groups. 1 bromo, okay, 1 bromo. So why didn't I still show stereochemistry here? Hopefully you guys can answer that. It's because this carbon has 1, 2, 3 electron groups, making it sp2 hybridized, making it trigonal planar. So my question to you guys is on 3, our isopropyl group should be on this carbon here. Is this also going to be planar, or should I show stereochemistry? So you're going to want to show stereochemistry. In this case, we don't know if it's R or S, but you could assign it either. I didn't ask for stereochemistry, but I'm just reminding you with 4 electron groups, 1, 2, 3, and then our isopropyl group, that would be an sp3 hybridized carbon. That's tetrahedral. That's when you have stereochemistry. So I'm going to put it on a wedge, and then for some extra practice, how about you guys tell me if this is going to be R or S? So go ahead, pause it again, and see if you can determine what it's going to be. And I'll walk you through it. All right. So 1 carbon at a time, remember. So we have our hydrogen. That's going back. We have carbon. We treat it as bonded 2 carbons and a hydrogen. Carbon, bonded to two carbons and a hydrogen. So right now those are tied. Carbon bonded to two hydrogens and a carbon. So in terms of our numbering here, hydrogen is going to be 4. This is going to be 3. Then what do we got? Carbon, carbon, carbon. But this one has a bromine. These only have hydrogens. So this one up here should be our 1. This should be our 2. So we go with our rules. We go 1, 2, 3, ignoring 4. Now we look at 4 because is it in the back? Yes, it's in the back. It looks like R. This is actually R. So if I were to ask you to name this, which I'm probably not going to ask you to put the letter in the name itself, but I could ask you if it's R or S, would be R1-bromo-3 isopropyl cyclobutadiene. Great practice. Feel free to do these, come back to this video anytime and try these again. All right. So we've briefly talked about things being primary, secondary, or tertiary, but let's kind of brush up on that for a second. We looked at different alcohols being primary, secondary, and tertiary, right? We said this would be a primary alcohol because it has one carbon group coming off of the carbon with our functional group. Those two hydrogens here. A secondary alcohol would look something like this because it has two carbon groups coming off of the carbon with the alcohol, one hydrogen. And a tertiary alcohol would look like this. So how we denote this typically, primary, secondary, tertiary. So it shouldn't be surprising that alongside the alcohol functional group, the halide functional group can also be primary, secondary, or tertiary. So if we have a chlorine here, this would be a primary alkyl chloride. This one here would be a secondary alkyl chloride. This one here would be a tertiary alkyl chloride. I don't know why I put that. I don't know what my brain was doing there. Tertiary. All right, so I'm going to draw a molecule, and then you're going to have to identify what type of alkyl chloride we have. All right, so here's a real, quote unquote, real example. I could give you a molecule that looks like this and be like, circle all the tertiary alkyl halides. So we want to look at the carbon attached to our halogen. In this case, our carbon has one carbon attached, two carbons attached. So this would be secondary. This one here, one carbon, two carbons. This would be secondary. This one here, 1, 2, 3 groups attached. This one would actually be tertiary. Being able to do that is very, very important for what we have coming up. Talking just generally about alkyl halides, giving you some history, why we care. These are very, alkyl halides specifically, are very common solvents. Things like chloroform, you've heard of. That's an organic compound with a chlorine on it. Dichloromethane, methylene chloride, few different ones. Reagents are used in all sorts of synthesis for things like drugs and things like that. Chloroform was actually used as an anesthetic a long, long time ago. Freons, so something interesting. When you attach a bunch of fluorines, which we typically don't talk about, to a carbon chain, it actually decreases its freezing point significantly. So if you have an old refrigerator, it probably runs on a chemical called freon. If you want to look up that structure, go for it. But there's a lot of fluorines, let me tell you. They have some pretty weird properties. Alkyl halides also have been used as pesticides. Feel free to look at those in your textbook. Other than that, I think that covers all the kind of fun information on alkyl chlorides. Let's get back to more things like that. More things kind of that I could ask you about. All right. So, structure of alkyl halides. We've actually already kind of covered this back here. We talked about size. Something we didn't talk about though is bond length. So, if you have room, feel free to just add to this. I'm going to use a clean sheet of paper. So, thinking about their sizes, chlorine and fluorine have a relatively short bond. They're both relatively small molecules, where carbon, excuse me, I think I just called carbon chlorine. Fluorine, carbon and chlorine have a little bit longer. Carbon and bromine have an even longer, and carbon and iodide, obviously these aren't to scale, have a really long bond. The longer the bond is, and this is an important one, the longer the bond is, the easier it is to break. Let's write that down. The longer the carbon halogen bond is, the easier it is to break. So I said earlier that alkyl halides are the most reactive. Excuse me. Alkyl iodides are the most reactive. Why? Now you can explain why. Their bond between the two, because of how large this molecule is relatively long. Therefore, it's relatively weak. And if something is weakly bonded, we could also call that it is reactive. So again, using all different words to describe very similar things. Of course, they all have dipoles. All of these are more electronegative than our carbon. So needing to know how to draw dipoles, they would all be pulling electron density away from our carbon towards themselves. I'm not going to make you memorize numbers or anything like that. The textbook has numbers. I don't care about that amount, that bit, as long as you have your general information. Don't really care too much about boiling point or densities. Let's review how we can make these alkyl halides. Spend a little time about that. There wasn't a bunch of questions on exam one about these radical reactions. Can I say that? Yeah, your guys' exam's already over. Um, but your second exam, it's showing up twice, and I haven't asked about it. I'd expect to see some more radical stuff on your second exam. All right, so I already gave it away, but how do we make these alkyl halides? Radical reactions. So if we take an alkane and react it with Cl2 or Br2 in either heat or light, abbreviated HV, we can add a halogen to the most substituted carbon. There, that is that word again. In this case, the different substitutions we have is secondary carbon, secondary, primary, primary. So it's going to add to one of these two. Doesn't matter which one, they're actually the same if you were to go to name them. So now we formed a secondary alkyl halide. I will go through the mechanism just so you can see it again. But you can do this with either chlorine or bromine to give yourself some sort of alkyl halide. So let's look at the reaction. The three steps for radical reactions are I for initiation. That's where we take our halogen. What did I just use? I used chlorine. Let's use bromine this time. We can either heat it or put sun on it, sunlight, some sort of light, to break these two electrons are being shared, one onto each bromine. That's called homolytic cleavage. When we do that, what we get out of it is two bromine radicals. And what a radical is just an unpaired electron. So typically electrons show up in lone pairs. This is an unpaired electron. We call it a radical. These radicals are very reactive. They like to do two different things. They will either abstract a proton or couple with another radical. For our propagation step, what we're going to do, we have let's use a different material this time. Let's use this as our alkyl halide. We have this, and now we've formed a bromine radical. It could either couple with another radical, which if we did that, it would just go back to this, so no point there, or it could abstract a proton. Here we have a few different protons to choose from. Each of these methyl groups has 3 protons it could pull from, or this carbon here, it could pull from that one. Remember about radical stability. The more substituted the radical intermediate, the more stable it is, and that's the path we want to take forward. So, are we going to form a methyl carbocation? Excuse me, methyl radical or tertiary radical? Of course, we're going to want to form that tertiary radical. So how we show that is that this one electron is coming over. It's going to want to form a bond. One of the bonds from that carbene-hydrogen bond is going to go and pair with it. That proton is going to get abstracted, taken out of our organic molecule, and our radical is going to end up on the carbon where we just lost our hydrogen. So our products for this would look like this. Now we formed a new bond between hydrogen and bromine because now there's 2 electrons being shared. Now we formed a carbon radical. What type of carbon radical? It is a tertiary carbon radical intermediate. For our last step is starts with a T, termination. In this step, we start with 2 radicals and end with no radicals. So now it's already abstracted its proton. The other thing the radical wants to do is couple with another radical. Now we generated this carbon radical. Our other equivalent, because we did form 2 equivalents of our bromine radical, can come and couple with this guy. So 1 electron from the carbon, 1 electron from the bromine. They, come and meet to form a new bond. So our product would look like that. We have now created an alkyl bromide. Take a second and see if you can name this alkyl bromide. Go ahead, pause the video. So hopefully we found the longest carbon chain. 1, 2, 3, 1, 2, 3. No matter how you count it, it's going to be 3. So we're going to have a propyl, or excuse me, a propane. Propane, 1, 2, 3. There must be a methyl group on 2, and as well as a bromo. So bromo comes before, B comes before M. So 2 bromo, 2 methyl, propane. Hopefully that was some good practice. Okay, that's when we don't have any sort of resonance. However, we've also looked at examples with resonance. So let's review that as well. All right. So when we have a molecule that has a pi bond on it, you will never, ever, 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 ever form a radical on a carbon with a pi bond. Please don't do it. Just don't do it. You're always going to want to form it at the carbon adjacent to the pi bond. That's because that radical then gets a special type of stability. Do you remember what it's called? So in this case, if we have a bromine radical, and it's going to want to abstract a proton, our radical would end up on that primary carbon. I know that this is secondary, but like I said, do not put a radical on a pi bond. I will mark it wrong. We always want it to go next to our pi bond. So when we form this new radical, it is primary, but it has a special name. It's called primary, starts with an A, allylic. And the allylic word means that it's resonance stabilized. Yes, resonance doesn't go away. So let's look at the other possible resonance structure for this compound. If we're going to do resonance with radicals, it's a little bit different than what we're used to. We only use half arrows to show the movement of one electron at a time. So if we're moving our radical to form a pi bond, it can't by itself. It would have to take an electron from the adjacent pi bond. So now those two could come together, form a pi bond here, where this one would now be placed on this side's terminal carbon. So let's look at what that would look like. So we formed a new pi bond here, but now our radical is moved over here. It is still a primary allylic radical. Let that sink in for a minute. Okay. Another way to do this, so this is just good to know. And I know if you're taking Organic 2 next semester with Dr. Naretti, she's going to use this reagent. If you want to do a bromination of some sort of alkyl halide, we're going to use resonance again here. Say we have this as our starting material. Instead of using bromine, which is a very toxic chemical, Niall Red, if you ever seen any of his stuff, very interesting. He does a lot of really not safe stuff, but he's actually made bromine. Very, very dangerous to use. So chemists don't like to use that. There's a much safer alternative called NBS. When you see this, and you will see it, do not freak out. It is the same thing as heat and light. So we can use NBS on this. It's going to do the same reaction as if it were to be Br2 and heat and light. So pause, practice. What would our products be for this reaction? You're going to have two products due to resonance. So give that a try. Pause the video. Welcome back. Hopefully you paused and got your practice. So let's look at our two options here. One option is that resonance didn't occur, and we've just added a bromine right here. Our double bond didn't go away, so that would be option one. Option two, and I will show the resonance, although at this point you should be able to do it on your own. Our intermediate for this reaction looks like this, right? We always want to form the most substituted radical intermediate. So this one is mono, di, tri-substituted, what we would call tertiary. It's a tertiary carbocation. Not only is it tertiary, because it's next to a bond, it's tertiary allylic. So if we go to do our resonance here, let's see what we get. So draw a resonance arrow here. I'll draw out the base structure. I'm going to use the other color to fill in what changed. All right. So these electrons here, this radical and an electron from the pi bond, came here to form a new pi bond. They just moved around, because remember, that's what resonance is. It's only the movement of electrons. That would leave our radical at this position here. So now we've taken our, tertiary allylic radical and made it into a primary allylic radical. At this point, we will care actually about major and minor products. At this point, I don't care too much. If I ask for more than one product, make sure you show both products. From here, our last step is just our bromine adding where our radical formed. So our other possible product for this reaction look like that. All right, let's keep on going. Of course, you can pause at any time as well. You need to catch up in notes. The nice thing about videos is that you can pause whatever you want. The benefits, you can pause whatever you want. The drawbacks is you can't ask questions. It's a trade-off. I'll be curious to see what you guys think after we try this out. Okay. So yeah, we haven't worked it yet. Okay. Now we understand what alkyl halides are. We understand how to make them. Now we need to understand how to react with them. But first, very short side tangent. Along with alkyl halides, you can also have what are called aryl halides. If you ever have a halide attached to an aryl ring, aromatic ring, not going to get into it. It's an organic 2 thing. It's no longer called alkyl because it's on this aromatic ring. We call that aryl, not alkyl. I will never ask about it, but you may see it in your textbook, so I just want to make sure you are aware of that. Okay, let's talk about nucleophilic substitution reactions. All right, let's break down what that means. Nucleophilic. So we should be thinking nucleo, sounds like a nucleophile, nucleophilic. Substitution, we're swapping something out for something else, and a reaction, it's a chemical reaction. So here's the general, put this in a fun color because it's important, general reaction scheme for a nucleophilic substitution reaction. You start with an alkyl halide of some sort. In this case, I'm not even going to specify. I'm just going to say carbon has the 4 bonds. We don't really care what's attached right now. We're going to treat that or react it with a nucleophile. It can just have a lone pair, or sometimes it even has a negative charge. That is going to go to form. Oh, this should have been, I'm so sorry. This should have been a halogen of some sort. I'm just going to put it as X. So we have this reactive alkyl halide bond. Remember, it's a polarized bond. This is more electronegative than a carbon, leaving a partial positive charge on our carbon. This nucleophile, I'm not going to show any arrows yet, but eventually we will, can attack that carbon, kick out our leaving group. So our product now our alkyl halide is left, and now it has the minus charge, and we have a new bond to our nucleophile. Obviously, this is with generic things, but it's a good kind of starting point. So this is the general reaction scheme, or even just general scheme for a nucleophilic substitution reaction. So next thing I want to talk about is elimination. So make sure you have this written down. Give you a second, or go ahead and pause, and then I'll talk about nucleophilic substitution. And then our definition of this, I'm not going to write down, but a nucleophilic substitution reaction, a nucleophile replaces the leaving group, or halogen here, from a carbon atom using its lone pairs of electrons to form a new bond with the carbon atom. So new bond formed, kicked out leaving group. That's what we see here. There's our kind of definition there. Leaving group might also be a new term for you guys. So for us right now, a halogen is a good leaving group. The halogen atom could leave with its bonding pair of electrons, so with this pair that's bonding, to form a stable halide ion. Remember, we talked earlier about how most halogens, besides fluorine, does a pretty good job of holding onto its negative charge due to both electronegativity and polarizability. Because it can hold onto its negative charge really well, we consider it a good leaving group. I will commonly abbreviate leaving group, capital L, capital G. As you can imagine, having an abbreviation, it's going to be relatively common. So last thing, before we move off this page, your pop quiz for today, the 28th, the code for that is 5829550. Please write that down and use that to get into the pop quiz for the 28th. All right, now let's look at elimination reactions. So for elimination reactions, when a halide ion leaves, another atom, commonly H+, forms a new pi bond. This is called an elimination. So that's in words. Let's look at what that actually looks like. So again, we're going to use the same kind of generic carbon structure. We're attaching it to some sort of halogen. X just represents a halogen, fluorine, bromine, or iodide, with an H here. So what happens is that our nucleophile, also known as a Lewis base, you've probably put that together by now, maybe, that nucleophiles and Lewis bases have very similar definitions. A Lewis base, what it can do is pick up a proton causing that leaving group to leave. So your product for elimination reactions are always, and there is no exception to this, an alkene. So this is our elimination. This will always form some sort of pi bond, either an alkene in this case, or eventually we'll learn ways to form alkynes. So let's look at a few practice problems. We're not going to do any arrows yet. We're going to do one practice problem, then we'll probably start to introduce those arrows. All right. So I'm telling you that this is going to be a substitution reaction. What would our product look like? Well, let's think about it. So what's our nucleophile? Well, here we have a sodium, but sodium, just like lithium and other metals, we don't care about them. We're organic chemists. We care about carbons and oxygens, nitrogens, hydrogens. Metals, we don't need them. So anytime you see a metal like this, especially in front of an oxygen, we call that a spectator ion. It doesn't really involve itself with the overall reaction. You see over here, it actually forms this NABR byproduct, which would be another inorganic compound having an ion-ion bond or an ionic bond. All right. So if this is just a spectator ion and this is a plus charge, there's no overall charge when I wrote this. So it must be our oxygen has a negative charge. If it has a negative charge, that would make it a good nucleophile. So our product, remember, substitution reactions, we're changing one group out, a good leaving group out, for a good nucleophile. So in this case, we would now add that whole group, OCH3. So congratulations, that would be the predicting, you have predicted the product of your first substitution reaction. It's unfortunate. Uh, okay. There are two different types of substitution reactions. There's what's called SN1 and there's what's called SN2. I'm going to teach you guys SN2 first because it is more straightforward in terms of arrow pushing mechanisms. The way the electrons flow is a little bit more straightforward in SN2 reactions. So for our SN2 reactions, this is the general scheme. We have some sort of nucleophile, and typically this has a full negative charge reacting with some sort of electrophile. In this case, alkyl halides are good electrophiles. Why are they good electrophiles? Well, think back to your definition of an electrophile. Something that has either a partial or full positive charge. In this case, our carbon, we've already talked about today, how this carbon, because it's bonded to a very electronegative halogen, has a dipole, leaving a partial negative over the iodine and a partial positive over the carbon. So this carbon is what we call electrophilic. It is electron loving. It wants more electrons. So in terms of arrows, you always start from electron rich to electron poor. That hasn't changed from resonance. You'll take your nucleophile, attack your carbon, and kick off your leaving group. So our product now we have a new bond to our nucleophile. All right, now let's look at a real life example. Say we have sodium hydroxide and one fluoroethane. How would the arrows look for that reaction? Take a second, see if you can figure it out. Find our nucleophile, find our electrophile, then try to predict your products. So sodium, just like we looked at earlier, when it was attached to this big group, is just a spectator ion. It has a positive charge, and we don't really care what happens to it. Our oxygen, on the other hand, that is our nucleophile. So one of the first things you should do when doing these reactions is identify your nucleophile and your electrophile. From there, you want to identify your nucleophilic and electrophilic atom. In this case, our nucleophilic atom is our oxygen, because that's what's carrying the negative charge. Our electrophilic atom is this carbon next to our leaving group, for all the reasons I just spoke about up here. partial positive. So with that, we look at our arrows. Our nucleophile attacks our electrophilic carbon, kicking out our leaving group. So our product now, remember our sodium, you can even cross it out if you want. I've seen people do that. I'm totally okay with that. Goes away. And what we're left with is that new group, that OH group has substituted for our chlorine. If you want, I'm not requiring this in any way, shape, or form, to combine your sodium and chloride or whatever two salts you have and at the products, go for it. I only care about the product that has the most number of carbons. So there's a few more things to know about SN2 substitution reactions. The first thing is the transition state. So we're forming and breaking bonds all in the same step here. That should sound familiar to the acid-base reactions. We had a question like that on our first exam. So let's look at what our transition state looks like for this reaction. Excuse me. So if we have a carbon, remember carbons are tetrahedral, they're sp3 hybridized. Let's use something different this time. Let's use, let's go back to sodium methoxide, OCH3. First step, identify our nucleophile, identify our electrophile. Our nucleophile is going to be this oxygen here. Sodium kind of goes away. We treat this as if it has a full negative charge, because in reality it does. Nucleophilic atom here. Electrophilic atom, chlorine's more electronegative than carbon. This is going to be partially positively charged. That's our electrophile. What happens in this reaction is that our nucleophile comes in from the, I apologize, I'm going off the paper here, comes in from the backside and does what's called a backside attack. I haven't had you draw a transition state before, but here we go. When you draw a transition state, you want to put brackets around it. I did define a transition state for you, though. Probably have to move to a smaller pen here. A transition state is kind of this theoretical position it can be in when bonds are breaking and forming all at the same time. So in this case, let's see what bonds are breaking and forming. We have our carbon in the center. We're breaking this carbon-chlorine bond onto that chlorine. So how we represent that is a dotted line. And as that bond is breaking, we have a new bond between our oxygen and our carbon forming. And of course, everything else is along for the ride. So OCH3. And then we still have attached to this carbon our other three hydrogens. So our transition state, remember when we did our diagrams, this is our little symbol for transition state. It looks like that. I've told you since day one, carbon should never have 5 bonds to it. And this is still the case. That's why we call this a transition state and not a real structure. This is this kind of theoretical thing that can happen, that happens to get to our products. So this comes in, forms a new bond. At the same time, this is breaking. Kind of has 5 bonds, kind of not. This is the way we show it. So this comes in, that goes out. When you do this backside attack, we get a unique feature out of it, but we're not going to get into that yet. We'll talk about that soon. But for our product for this one, if you weren't able to predict it, it would look like this. I'm not going to show any stereochemistry here. but we will talk about it soon. So now we've replaced our, oh, excuse me, that is not it. We now have a new bond to our OCH3, because that's what formed the new bond, kicking out our leaving group. Okay. So let's talk about the rate of this reaction. So it's called an SN2 for a reason. It's because the rate of this reaction is equal to two different things. It depends on two different things, I should say. So rate equals K, which is just some constant. This isn't general chemistry. I'm not going to make you calculate the rate constant. K times the concentration of your alkyl halide times the concentration of your nucleophile. So the two comes from the two different things the rate of this reaction depends on. Remember, K is a constant. That doesn't change. But we can adjust the amount of alkyl halide or the amount of nucleophile. Let's look at an energy diagram for this reaction. Or actually, let's do a few examples of how I can ask questions about this, because I will ask a question about this. If we're looking at an SN2 reaction, and the rate is equal to alkyl halide times the concentration of alkyl halide times concentration of nucleophile, what will happen to the rate when I double the concentration of nucleophile? Give me a second to think about that. If we look at it mathematically, go ahead, pause. If we look at it mathematically, what's going to happen? Well, we're just taking this, multiplying it by 2. That's going to make this double. Everything else is just multiplication. So it's going to double the rate. I could ask about, what if I times it by 4? What if I divided it by 4? I could do a bunch of different things to modify our rate. So knowing how this plays in is important. So what will happen to the rate? I remove half of our alkyl halide. Take a second to think about it. Go ahead, pause. So if we remove half of the amount of alkyl halide, we're just dividing by 2. Everything else is multiplication. So we're just dividing the whole thing by 2, so the rate would half. Relatively straightforward math, not too tricky. But knowing this is something I would expect you to know. And again, you are given this because there's only two things in the reaction, your alkyl halide and your nucleophile. In SN2, the rate depends on two things, both of them. So now let's look at our energy diagram for this reaction. So hopefully you were able to label this correctly on your exam 1. Energy is on this side. Reaction coordinates on the bottom. We want to start at some energy level. We're going to end at some energy level. I don't care if it goes up or down. Not super important right now. But of course, do we have any intermediates for this reaction? Do we have any carbocations, any radicals? The answer is no. All we have is a transition state. So our reaction energy diagram, reaction coordinate diagram, could be one transition state, and then it going to products. So this side would be starting material, This side would be products. This would be our transition state. Starting material, products. So let's do an example and put things where they belong. So say you want to do this reaction here. Ah, Professor Hallstar, what is that? Sulfur is I'm not used to seeing sulfur. Don't panic. Stop. Don't panic. Sulfur is right below oxygen on the periodic table. It's going to act the same way. So again, sodium treat we like we have a plus. The sulfur we treat like we have a minus. That's going to be our nucleophile. We have our electrophilic carbon here because of the dipole between the bromine and the carbon. This can attack, kick out our leaving group, and then our product would look like that. Okay, so now with my pencil, because space, let's put these in the places where they belong. So our starting material, well, that's just these two things. We have our alkyl bromide, and we have our sodium sulfur methyl. I'm not going to ask you to be able to name that. That sulfur a little bit bigger though. So that's our starting material for this reaction. The products, well, we have this. I only care to see this. If you want to put the Na and Br together, you can. I only really care about this, so just putting this is fine in my opinion. But where did this methyl go? Remember, line angle formula, the end of this line indicates a CH3. That's where the methyl went. Now, something I'd expect you to do, be able to do, is draw the transition state. So if you have to draw the transition state for this, what would that look like? I got a little bit of space. So during the reaction, our transition states always go in brackets. We have our little transition state symbol. We want to show the bonds forming and breaking at the same time. So what's being attached? We have a carbon here. So you can draw out your carbon. What's attached to that carbon? We have a methyl. And we have two hydrogens. What are we breaking? Okay, we're breaking our carbon-bromine bond. So it's going to be our dotted one. And we're forming our new carbon-sulfur bond, and everything comes along with it. So CH3 sulfur. So that I'd expect to be able to put up at our transition state. So for this one, I'm just going to highlight it up here and then highlight it down here because there's not quite enough space. Hopefully you guys feel okay with that. Too much time we got left. Still got some time. Okay. Let's keep going. Actually, let's probably do some practice, eh? Let's see what we got. Okay, before we do some practice, there's a few things, a few vocab I want to throw at you. Need to throw at you. SN2 reaction is a concerted mechanism. Great. What the heck does concerted mean? Let me tell you. A concerted mechanism is a reaction that occurs in a single step. So what do I mean by that? There's no intermediates. You go from starting material, transition state, products. That's it. No intermediates to consider. With radicals, thinking back to that, we did have that radical intermediate, which had different levels of stability. With SN2, we don't have to worry about that. There is no intermediate. It is just a transition state. There's a bunch of different concerted mechanisms you're going to learn throughout our time together, and then if you wanted to take organic too. So knowing this, what a concerted mechanism is, again, I'm going to underline it, is quite important. All right, let's talk about the stereochemical. Well, do some practice, and then we'll talk about the stereochemical concerns. So let's do try those three. I'm going to pause for a minute, and then we'll talk about them. All right. So hopefully you took some time, answered these questions. Again, take it kind of slow here. We want to figure out our nucleophile and electrophile. Nucleophile, we're looking for extra electrons that can be donated. Our sodium has a plus charge. Our oxygen has a minus charge. Because of that, this can act as our nucleophile. Great. So we found our nucleophile. Now we got to find our electrophile. Our electrophile in this case, carbon, chlorine. Chlorine is more electronegative than the carbon. We could draw a dipole. Carbon with its partial negative. Excuse me, chlorine with its partial negative. Carbon with its partial positive. That carbon is our electrophilic atom. So the arrows for that, I'll use orange. Nucleophile, electron rich to electron deficient. When we push electrons to that, we can't have 5 bonds at a time. Something's got to go. What's going to go is our good leaving group, that chlorine. So for our final products, we've now formed a new bond between this carbon and this OH. Hopefully you guys got that one. Try the next one. Again, first step, identify your nucleophile and electrophile. In this case, sodium plus charge. And it doesn't have to just be a sodium here. It could be a lithium, it could be a potassium, it could be a magnesium. Well, magnesium may be a little bit tricky, but sodium, potassium, lithium are very common ones you're going to see. If that has a plus and there was no real charge at the start, this oxygen have to be a minus. That would be our nucleophile. Remember the definition of nucleophile, something that can donate electrons to an electron deficient species. In this case, where's our electron deficient species? It's here, but where specifically? Iodine is electronegative, so it can pull electron density away from this carbon, leaving it with a partial positive, thus electrophilic. It wants electrons. Nucleophile attacks electrophilic atom, kicking out our leaving group. Remember, always go from electron rich, where you have a negative charge, to electron deficient, where you have a partial or full positive charge. Our product, 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. And then we formed a new bond to this oxygen. Did we break any bonds off of this oxygen? No. Everything else comes along for the ride. So we still have a CH2, CH, and 2 methyls. So our product would look something like that. I'll talk about our last one. Again, sodium, you cross it out, you can do whatever you want with it. Sulfur just below oxygen on the periodic table. It's going to be a nucleophile. So we found our nucleophile, our sulfur, our electrophile is going to be this over here. What part? Our carbon next to our leaving group. For the same reasons I've been saying. It's going to have a partial positive due to the inductive effect or the fact that this is more electronegative, that dipole here. We always attack from electron rich to electron deficient. We can't have 5 bonds to a carbon at a time, so we have to kick out our leaving group. So our final product would look something like this. 1, 2, 3, 1, 2, 3. We formed a new bond to sulfur and this methyl group. Sorry, I didn't change colors there, but I think you guys get the idea. Hopefully this makes sense to you. There are a ton, I mean a ton of practice problems for this type of stuff. All right. So let's say, give you another type of problem I could give. What reaction could we use an SN2 reaction to form, move my paper, this type of product? What 2 things on this side would react to give me this? Pause and give it a try. This is the first time we've looked at something like this. So if you don't want to give it a try, you should. But let's see how we would approach it. So I see 1, 2, 3, 4 carbons. So on our starting side, we had to have 4 carbons. We end up with an OH. So that means our base, excuse me, our nucleophile was likely some sort of hydroxide. So we likely use sodium hydroxide because what we ended up with is an alcohol, a nucleophile, Then come in and displace something else. So what was likely here, 1, 2, 3, 4, the only leaving group we've talked about so far is some sort of alkyl halide. So it could be iodine, could be bromine, could be chlorine. 2, 3, 4. Did I add too many carbons? 1, 2, 3, 4. I did. Sorry. That carbon isn't there. 1, 2, 3, 4. If you don't believe yourself, check yourself. Nucleophile with its lone pairs could attack here, kick off our leaving group. Sure enough, that would be 1, 2, 3, 4 carbons with an OH on 4. 1, 2, 3, 4 carbons. Now it's carbon 1 because that's our most reactive functional group. So I could ask it either way. Hopefully that makes sense. Okay. For SN2 reactions, you might have noticed a trend here. We always use a nucleophile. I'm going to say 99% of the time, we use a nucleophile that has a full negative charge. So for SN2 reactions, we use a nucleophile that has a full negative charge. That's because full negative charges are, we've talked about charges before, the more charges, the more reactive, the less stable. So by having a full negative charge, you are reacting better. For SN2 to have it happen in one step, you have to have a really strong nucleophile. So some examples of stronger nucleophiles could be things like sulfur with a negative charge. We've seen that one. Oxygens with a negative charge. You could have a carbon with a negative charge. You could have groups like, although, we'll stick with those ones for now. There are other ones, but that's okay. These are some good ones to start with. But you're typically looking for a full negative charge. So if I want an SN2 reaction to occur, and I have a choice of two different starting materials, what starting material do you think I should pick? So I want one of these two to react with this compound to form this. I can either use this, oops, or this. Which one would react better for an SN2 reaction? Hopefully, you said this bottom one. Why? It's stronger. This only has lone pairs, not a full negative charge. This is a full negative charge. This is a lot more reactive than a neutral water molecule. I mean, think about it. This is drain cleaner, and this is water that we drink. We don't go around drinking drain cleaner. It's too reactive. Um, can attack, kick out our leaving group, form our product. So this one would react a lot faster for an SN2 reaction. There's a bunch of trends I'm not going to make you memorize, but have at least know about charge. That's one I do expect you to have a good handle on. Something else that can affect how good a nucleophile is. So something else that can affect how good a nucleophile is how bulky it is. So what the heck do I mean about bulk? We've talked about steric hindrance before. Remember our chairs? We want our large groups, our bulky groups, to be on the equatorial position to avoid steric hindrance. Well, if you have a nucleophile that's very bulky, it is not going to want to do that backside attack. So let's look at an example here. Again, say we have this carbon here. This alkyl halide. And we need to choose a nucleophile to do this SN2 reaction. We want it to either be, well, we can't really compare here, but we'll just say products. Say SN2. So what's going to be better to use here? What's less bulky? This or something that looks like this? Is our 1, 2, 3 propyl group bulkier or our T-butyl group bulkier? Hopefully, this is relatively intuitive from what we've learned. The T-butyl group that has a bunch of different carbons off of one carbon. This is a relatively straight chain. This is a big bulky group. This is what we call T-butoxide, and we're going to be using it a lot for a different kind of reaction. But it will not do SN2 reactions. It is too bulky. Not backside attack. All right. Hopefully you feel okay with that. There is one last thing I want to talk about today. You know what? No, you guys worked hard. I'm gonna let you guys go for today. Um, the code was in here. If you missed it, go back and watch it again. Make sure you take your pop quiz so you get those points. Um, yeah, for the pop quiz, you'll see it's nothing to be afraid of. It's just making sure you're watching the videos and paying attention. Other than that, if you have any questions, let me know. I hope you have a great rest of your week. It'll be Wednesday for you guys, so hopefully you've recovered from your exam and ready to get back into it. Um, I will have a video for you tomorrow. Enjoy the rest of your day.